Okay, here we're looking at sound. And sound waves are compressional waves, so they're not the transverse waves that look like this. They are compressional. Sound waves are patterns of compressions and rarefactions of the molecules, so solid, liquid, or gas, that the wave energy is moving through. So what that means is that here, just this little diagram, I'm showing you that these are the areas of rarefaction. It's the in-between parts here, and then the thicker lines are areas of compression. So this horn or whatever is making this noise sends out a vibration of energy, and what it does is it moves the air molecules that are all around us. So we're surrounded by air molecules, and that sound pushes them in a certain pattern. So it's a pattern of compressions, areas of compression where the air molecules are dense, and then areas of rarefaction where there are less air molecules. And this is kind of like the code for the specific sound. And this moves out in all directions, not just in these 2 dimensions here. It goes in all directions around this horn. Now, the speed of sound, the speed that a sound wave travels depends on the medium. So if it's a solid, liquid, or gas, and the temperature. So 2 things determine the speed of sound. What is it moving through, and what's the temperature of the thing that it's moving through? Sound waves travel faster in solids and liquids because the molecules are closer together than the molecules in a gas. So these are just patterns of the air molecules themselves. The air molecules here are squished up, kind of like this would be areas of traffic jam. And then the air molecules here, here, and here are less trafficked. Oh, there's a happy birthday balloon floating in the way. So this would be areas where like the air molecules can move freely. There's not a lot of air molecules. This would be like air molecule traffic jam. So when the molecules are closer together, the wave energy can travel faster through them. So that's why solids and liquids can pass sound energy faster, because the molecules are closer together, so they can pass that energy wave faster. Sound waves travel faster when the temperature of the medium is higher, because the molecules are already moving faster and therefore can transmit the compressions faster. So if you're in a liquid, if you're in water, warm water will transmit the compressions faster than colder water. So sound is going to travel faster in warm water and slower in cold water. Okay, now we're going to look at how humans hear. There's 4 steps to human hearing. Step number 1, the ear gathers the compression wave pattern as it moves through the eardrum membrane. So the first step is your eardrum, and it's a membrane that's going to kind of vibrate like a drum, depending on the pattern of compressions and rarefactions. So it's kind of like a barcode or a pattern of 1s and 0s. And the way this works is inside of your ear, there's something called cilia detector cells. Cilia detector cells. And these are little cells that have cilia on them, kind of like little hairs. And those detect the pattern as it moves through. So they move back and forth depending on when these areas of compression hit those, or the areas of rarefaction. And those cilia detector cells, those hair cells, can actually die. It's natural for them to stop working as you get older, and they don't replicate through cell replication, through mitosis. They don't actually replicate. So once they're gone, they're gone. And you can damage these cilia cells through loud music, or just age kind of deteriorates these. So once they're gone, they don't come back. So just be careful of that. Number 2, the bones of the middle ear, called the hammer, the anvil, and the stirrup, they act like amplifiers. So once that sound passes through your eardrum membrane and it hits these bones actually act like an echo chamber. So it's like a bone echo chamber where the waves are bouncing on and off of these bones, and it acts like an amplifier. So it amplifies the sound. And then number 3, your inner ear cochlea vibrates and sends the code to the brain. So this is where you connect the ear to your brain. And the certain vibrations, the code that gets sent from the cochlea to the brain, they go in the form of auditory nerve impulses. So these nerve cells, we know that nerve cells connect using electricity. They send electricity signals between them. So this happens really, really fast since it's traveling by nerve signal to your brain. And then number 4, the brain decodes and interprets the nerve impulses, and that's how you get sound. These nerve impulses, they travel much faster than hormone messages. So when a message is sent from your ear to your brain in the form of a nerve impulse, it travels a lot faster than like your eyes. Your eyes actually use chemical, hormonal signatures, impulses, to send that information to your brain. So your eyes send information to your brain in the form of hormones, and your ears use nerves. So you can actually, your brain processes sound much, much quicker than your eyes process light. So this is why your eyes will turn a series of like still images into a movie. So you know those flip books, it's just a bunch of individual still pictures, but your brain interprets it as a moving thing because it's actually pretty slow. Your eyes are processing those pictures pretty slowly, slower than your ears. Okay, now we're going to look at the difference between intensity and pitch. Intensity is the energy, also called the amplitude of the wave. So the amplitude of compressional waves, it's not how up and down it goes, but it's actually the thickness of the compressions. So this wave here, this sound wave, has a larger amplitude because the compressions are much larger. So we're going to say this is a higher intensity, and this is going to give you a loud volume. And we're going to compare that over here to these areas of compression, which are smaller amplitudes, which will give us a lower intensity and a quiet volume. All right, pitch over here. Pitch is the frequency of the wave, and this is measured in hertz. Frequency is measured in hertz. And this is going to give us either high notes or low notes, a high pitch or a low pitch. And this does not depend on the amplitude, so I tried to make the amplitude pretty much the same of the compressions. That's the size of the compressions. This is actually the number of compressions that are passing per second. So intensity is the size of the compressions, pitch is the number of compressions that pass. So this example here shows a higher frequency. The compressions are coming more frequently. More compressions per second, that's going to give us a high pitch or a high note. Over here, these compressions are coming less frequently, so this gives us a lower frequency, less compressions per second, and a low pitch or a low note. Here is just a little chart that shows the threshold that humans can hear measured in hertz. So humans can hear between 20 and 20,000 hertz. Subsonic is less than 20,000 hertz, so this would be like a dog whistle. Dogs actually have can hear over in this section, we can't. And then ultrasonic over here is greater than 20,000 hertz. We would not be able to hear this sound. All right, one more thing, Doppler effect. Okay, the Doppler effect is the reason why if you ever hear an ambulance or a fire truck, if you're standing still and the ambulance moves past you, you all have noticed that as the ambulance is moving toward you, it's a very loud, high-pitched sound. And then as the ambulance passes you, it gets to a lower pitch sound. So the reason why that happens is that, I'm going to explain this little diagram here. So here we have a stationary ambulance, and then the siren's on. It's just sending out sound waves from a stationary stance. Once we start moving that ambulance, the front of the ambulance is going to compress the sound waves in front of it. So as the ambulance is moving forward, it's compressing the sound waves. And this is position A. So we're going to talk about the sound at position A, what you hear, versus the sound at position B, behind the ambulance. So if you're standing in front of the ambulance and it's moving toward you, you're going to hear shorter wavelength sounds that have a higher frequency and a higher pitch because these sound waves have been compressed at the front. So we get a higher pitch, higher frequency, shorter wavelengths. Now once the ambulance passes you and now you're behind the ambulance, it's moving away from you, the sound at position B, you're going to have longer wavelengths of sound back here with a lower frequency and a lower pitch. So that's why when an ambulance passes you, it's really loud at the beginning and then it tapers off as it passes you when you're on the backside.